Okay, so let's start with the chain rule. You know, the chain rule is a derivative of compensations. Earlier we learned, last semester we learned chain rule for function of one variables. Now we have more than one variables. So in this context, how the chain rule looks like. Okay. Okay. Recall that when you have chain rule, so for example here, y is a function of f a function of x, while x is function of t. So indirectly, f is function of t. So you take derivative of f with respect to t. So this is equals to df over dt. Okay, but f is a function of x. So derivative with respect to x times derivative with respect to t, x, right? So I call chain because somehow looks like the tx may cancel and leaving you at just dy over dt. Okay, so that's one variable. What happened to two variables? Okay, so let's look at the theorem and let's make some simplified view of it. Okay, we have x is a function of t, y is a function of t, right? You have z, or f is a function of x and y. Okay, so in directly, z is a function of t indirectly, right? Because x by t. So you can take derivative of z with respect to t. This is just one variable derivative. So it'll be z over dt. Okay. So how to take derivative? Well, like the z over something times the x over dt. So, but here you have dx. But x is just one of the variable for z. So when you take derivative with respect to z, it should be partial derivatives. And same thing you do to c over dt, so you get this one. Okay, so then it looks like I'll write this in detail later. So this looks like a gradient of z, okay, times a vector called dx dt, right? Dot product. Okay, or schematically, it looks like this one here. We have a z is has variable x and y. Okay, while y is x is a function of t, y is a function of t. So when you take derivative from z t, there are two ways to compute this one. Going this way, when you see dz over dx, right? X over dt, sorry, this one, plus the second path. So dc over partial for y, dy over dt. It looks like in this diagram. Okay, so let's write it down. All right, so this is how to remember this rule. Okay, so z going down to x, you have dz over dx. Going down to y, you have dc over dy. Okay, and coming down here, the t, this is dx dt, f dy dt. So going this way, going this way. Okay. So that means this one. Point is differentiable. Therefore, partial derivative exists. Okay. And x of t and y of t also differentiable. Then the c over the, sorry, the t is dot uh, gradient dot and d of dt dy dt. Okay. Schematically, oh, I should write this one. Yeah. So this is d dx dx dt plus dt. And schematically, you should get something like this. Okay, so let's do some example. Or just show you the example from the textbook first, and then let's compute on the from the exercise. All right, so z is x cubed times y. X is 2t and y is t squared. So we'll compute the z over dt. Okay. So just look at this schematic diagram. Okay. And looking from this diagram, you see that from z to t, there are two ways. So dc over dx, dx over dt plus dc dy, dy dt. We'll compute each one. Dc over dx, so 3x squared y. Dx dt is just 2. Dc dy, respect to y, you have just x cubed, and dy dt is just 2t. So in terms of t, so you have just substitute x equals to t, y equals t squared 2, and you get. All right. And you may also as well just substitute the x and y. So write substitute t to x and y from the beginning. So you get z is a function of t. Here. Z, you substitute 2t to the x, you get this. substitute t squared to y. So you can directly compute dz over dt, and you get the same thing as this. Okay. This is just an example. Solid right circular cylinder heated, radius r, and height is h increase. All right. So the radius, so it extends, as well as the height extends. Okay. But at that instant, when r equals 10 and h equals 100, r is increasing at 0.2, and h is increasing 0.5 per hour. How fast is s increasing at this instant? So we're asking about the SDT. Okay. And well, we know that the S is the surface area. Okay, so surface area, you see that surface area, this is 2 pi r times h. So the circumference, 2 pi r times the height, okay, plus the top and the bottom. Okay, so the lid, bottom lid and top lid. So 2 pi r squared. Okay. So now we need to find the SDT. So using chain rule, so the schematic looks like this one. S, function of R and H. So both are function of T. Okay, so the S dr, the R dt, and the S dh, the H dt. So this is how you get it. Okay, and then substitute. Okay. And then you get the number. All right, so let's before going to example from the exercise, let's just extend it for 3 variables. Nothing different. We just need the one more variable. So W, you have 3 variables, X, Y, and Z. So each of X, Y, Z is a function of theta, for example. So one variable. So when you take derivative from W to theta, okay, you have 3 paths from W to theta. The left one, so W, oh, sorry, dW over dx here, that's dx d theta. So the middle path, dW over dy, dy d theta, and left. So theta. That's the only difference. Okay. Before going there, let's do this one here, the chain rule. All right. Here's the difference here. Slightly different. X is also 2 variables, S and T. Y, and T. Okay. So let's see. So Z is a function of X and Y. So X is function of S and T, then T. So the schematic is the scheme. Let's see what's the scheme. No, data profile scheme. All right, so let's note. Of more than two variables. Okay, so for example, C is a function of X. The W is a function of X, Y, and Z, while X is a function of T, Y a function of T, and Z a function of T. Each W, X, Y, Z are differentiables. Okay, so here the scheme, the diagram, sorry, I should say diagram, not scheme. So press W here, you have X, Y, Z here, and you have T at the bottom. Okay, so here we have compute. Okay, so the W, the X, the T, so the left path, the middle path, and the, sorry, at the left, sorry, the right. Okay, as long as you can write down the diagram, you're safe. Okay, so another version of chain rule is this one. Suppose we have, say, W is a function of X and Y. X is a function of S and T. Y is a function of S and T, like this. Okay. So indirectly, A and W is a function of S and T. Okay. So we, from this, we question is fine. Yes. So now schematically, we have something like this, a diagram. So W is a function of X, okay, and a function of X is a function of S and T. Okay. While here you have okay. On the other hand, it's okay. So then you can get easily from here. So assume differentiability. Okay. So now you can compute W over the S. Okay. So there are two ways how to compute from W to how to proceed from W to S. So first, dx, yeah, and then S. Okay. And second is y and y over dx. Okay. Same thing, dy over dt. The t is this variable here. So first, the blue one would be y over dx through x and through y. So this is changeable. Oh, whoa, whoa, whoa. Okay. Now, okay. And let's pick some example from the exercise. Implicit functions later on. Let's go with the implicit function later. Okay. For example, here, number 13. Okay. Okay. So z is the function x and y diagrammatically. So x is a function of s and t. Y is also a function of s and t. So we have s, t, and okay. So the z over dt. Okay, so this one. So over dt is through x and dx over dt. Okay, and through y is y over dt. Okay, so let's compute this one. dz over dx, z over dx, so 2xy, dx over dt, so 2, That's dc over dy. Dy over dt. Uh, so minus 2st. Okay. And now you want to add dc over dt. Plug it in. Okay. Uh, Sorry, I should uh, still substitute this one. Okay, sorry. So 2x is 50 plus s times 2 plus x squared minus 2. Okay, so ft st. Okay, so plug it in here. Okay, let you finish that one. Okay, questions? All right. Okay, let's go back to the. I just go over quickly on the implicit functions. Here we go. So suppose you have f of xy defined 0 defines y implicitly as a function of x. So in these expressions, y is a function, x is variable. Okay? But the thing is, it is difficult to compute. So you still can find dy over dx. Okay. All right. So let's take this derivative with respect to x. So the f dx, 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 df dy, dy dx. Okay. So you have solving for dy dx. You get this df dx, dx, this is 1. Okay. So df dx minus over df dy. So this is another chain rule. Okay. For example, this one here. So you need to find dy dx given this say a curve defined by this x cubed plus xy minus 10y cubed equals 0. Now, because there's a quartic power 4, it is in general it's impossible to find y explicitly. Okay. However, you still can find dy dx. Okay, so dy dx. So let this is the f. So this f. That is the f. Okay. So this have a form f equals 0. Then dy dx is we get from here. So you can compute this one. Okay. So another way to do this, just take derivative with respect to x in this both sides. So you get this one. and solve for dy over dx. It gives you the same thing. Okay, so this is similar calculations. You have dz dx, df dx, df dz. Okay, dz dy is this. All right, so let's do one more example. Problem 20, so the last one here. So word problem. Not this one. Ah, so here's the problem. Sand is pouring into a conical pile in such a way that certain film the height is 100 and increasing at 3. So this is a pile of sand. So this is a pouring sand 3. Sand. This is the shape. Okay. So you have here 8. This is R. Okay. At some instant, when the height is 0, okay, height is 100, increasing at 3 inches per minute. Okay. So what it says that the h over the t when h is 100 is 3. Okay. And the r over the t, okay, when base is for base radius, so r is 40, is 2. How fast is volume increasing at the time, at that instant? Okay, so we know V is volume. 1/3. Sorry, 1/3 pi r squared, right? Times the height. All right. So here V is a function of R and H. So the question is, how fast is volume increasing at that instant? Okay, so dV over dt when well, H is 100, R is 40. Sorry, hold on. My OneNote stuck. Yeah, everything's stuck. Let's just stop here anyway. So it's, let's see, can we get it unstuck? No. All right. A bit too much, I guess. So I'll complete this. I'll complete this example before sharing the notes. Meanwhile, I'll see you then on the problem session this coming Thursday. All right. Thank you. Have a nice day, and I'll see you then next time.
All right, thank you, sir. Have a nice
Thank you,
day.
sir.
Thank
Thank you,
you.
Thank you,
sir.
sir.
Stop.